Well, hello and welcome. This is Dr. K, and today we're going to be talking about datums. All right, so today I wanted to talk to you a little bit about datums, or datums, or datums. Well, however you say it, it's a potato, potato, aluminium, solder sort of thing. But whichever way you look at it, datums are going to be the foundation of our drawings that's going to allow us to show our design intent. All right, design intent. Well, what's design intent? Design intent is how you, as the designer, intend for the part to be used. Is also kind of a way of how you express how you intend the part to be produced. So a datum. A datum is going to be a reference feature or feature of size. And so we've talked about features and features of size, and so we're going to use those features and features of size as datums. So what's that look like? Well, here we have we'll start with a part, and what we want to understand is this part in space has 6 degrees of freedom as it sits. So what's that mean? Well, we have our translation, so we can translate this part, and it can go up and down, and we can rotate this part. We can rotate, we can rotate, we can rotate. As the designer, we need to decide how we're going to lock this feature down in space. And so to do that, we're going to decide what features are going to be used as our primary datum, what features are going to be used as our secondary datum, and what features might be used as our tertiary datum if needed. And you'll see what that looks like as we kind of go through some of these examples. So for a part like this, we can see we have all kinds of space, rotation, we can do whatever we want. So the first thing we need to do is we need to lock this part down with one of the features. And for this example, I'm going to start by just using planar faces. It's one of the easier ones to understand. And so what we have here for a part like this is we have nice flat planar faces that we're going to use, or that we can use as our datum. And so when we decide that, hey, we're going to choose this surface to be our primary datum, that locks that feature down onto a reference frame. So on the table here in my example, what that looks like is we've locked this part down onto the table, and since we've done that, we've reduced some of the degrees of freedom. Now, if I keep this part on the table, all we can do is translate back and forth, left and right, and I can rotate. That's all that I can do with this part. So we've really started to set up a reference frame for this part. Well, since we can still rotate and still translate, we need another reference plane. And so let's use this plane as our example. So I'm gonna take this little part here, and we're going to use this. This is going to simulate our datum. So we're going to now push this part up against that datum. So here's our datum surface. We now have our first datum, that's our primary. We now have a second datum, that's our secondary. And now what do we have? This part can only do this, right, against that datum reference. So what do we need? Well, we have a translation we need to take care of, so we need one more datum reference. And for an example like that, I might use this part as our tertiary. So now that we pushed up against that part, we are no longer able to move this part in space, and so we've established our datum reference frame. So here I brought this part out to kind of give us an idea of what the datum reference frame looks like when we talk about the primary, secondary, and tertiary datums. We really talk about establishing first that primary datum, which really is a plane. It's 3 points. And so that's why we have 3 points here. If we were to look at a part and establish ourselves on that datum reference, and of course this part is too small for this here, it's really establishing on that bottom flat plane. So that would establish our first datum. Our second datum, our secondary datum, is a 2-point datum because we really only need a line to establish that second degree of constraints. And I think it's kind of showing here, but if we have our 3 points down below and our 2 points here, that tertiary datum really is only a singular point, which is what we have over here. We're just going to be touching a singular point. That's all that's necessary to restrict that last degree of freedom of motion. So what's that look like on a drawing sheet? What do datums look like on a drawing sheet? So here you can see a 3-view drawing of a part. This part contains a datum A, a datum B, and a datum C. You can see that those are surfaces that associate with the part right here. If I was to pull out this part, we can look at the part and see, okay, datum B is this surface here, datum A is this surface here, datum C is this flat surface here. And so that's how we are going to identify those parts. Using those 3 planes as datums for this part does establish our reference frame. It locks this part into space. And so now that we've locked the part into space, we're going to be able to start referencing features with respect to that reference frame. Another thing to recognize is that how many degrees of freedom actually get constrained when we select a feature or feature of size, and does every reference frame, does the part itself need to be completely locked in space? So let's take this very, very simple part. It is just our cylinder. We may look at this part in a sec, but for it, if we were to reference a datum reference frame to stop this thing from orienting in space, I hope you would first see that this cylinder would be a great feature. Of course, it's a feature of size. It's a regular feature of size. So we can grab on to that, and that locks down our reference frame. If we grab onto this feature, what can happen? This feature is still allowed to move back and forth, and this feature is still allowed to spin. A second datum reference on either of these faces is going to lock down this part so that it can no longer move this way, but the part can still rotate. So the question I'd have for you is, if this part can still rotate in space, does it matter? Well, there's no other features on this part, nothing else is going on, and so if this part can rotate in space, I would maintain that it doesn't matter that there isn't an extra datum reference. And honestly, with the features here, if you notice this part, we can reference this feature, we can reference this feature. There's only one other feature to reference. And if we've already referenced this one to lock this space, referencing this feature doesn't change that. All it does is do what's called over-constraining our part, and that's one thing we want to try to avoid. On the other hand, a part like this, it may matter that we lock this part down in all degrees of freedom. So again, we could use our cylinder here as a datum reference. That locks us into space here. We could use a face here to lock us in our translation this direction. And then we have this spinning to deal with. Now maybe to deal with this spinning, we would use this as our datum reference, this feature here. Maybe we use this feature here. Maybe we use this feature here. Any of those features could lock this down in the rotation to get us a singular reference frame. Is it necessary? It depends on your part. And so that's one thing that you're going to have to really start to think about is what does it mean to lock down our part in space, and is it necessary? We do need to be aware that as we deal with this reference frame, this ABC, ABC is just an indication of what feature is being used. When we go and use our datums to set up a reference frame, we're going to use something called a feature control frame. And that feature control frame is going to be attached to some other feature, because ultimately what we're going to be doing here is we're going to be referencing a feature. I'm going to use this one here. Let's say this whole with respect to that feature, with respect to that datum reference frame. And so at the back end of this feature control frame for a part like this, we're going to see 3 boxes. So we're not going to worry about this. This will have some other information in it. But we're going to have 3 boxes. The first box is our primary. The second box is our secondary. And the third box is our tertiary datum. Now for a part like this, we might look at this whole and say, okay, we want a primary datum of A. We want a secondary datum of B. And a tertiary datum of C. Now that establishes a certain reference frame with respect to this drawing. And then with that reference frame, we're going to be dealing with the position or the location of this whole, orientation of this whole with respect to that reference frame. But what I want for you to understand is the order at which these occur has everything to do with how you want to set up the reference frame. So if you deemed it more important that you wanted your primary datum to be feature B would be placed into the first slot. If you wanted A to be your secondary reference, then you would place A in the secondary slot. And then C would finish off that feature control frame. And it could be any combination of these A, B, and C. It is solely at the discretion of the designer to try to relay your intent. Here we have another part, and hopefully you can see I have a datum A, B, C. If we were to set this into a feature control frame and deal with our 3 primary, secondary, and tertiary spots, we can do the same thing here. Now in this case, I've replaced datum B from being this plane to being a circle. So it still could look the same though. Here we have A. A is still primary for me, let's say, because that's very, very important. But maybe I don't, after A, I want the 2 points. I want that to butt up to C. So C might be my secondary reference. And then B, being that it's a circle, we're going to remove that last degree of freedom. We might label our tertiary datum as B. So with this datum reference frame, we're really talking about this corner being important, and the dimension or location and orientation of these features with respect to that point is important for the design of this part. Now for this second example that we went through here, now we're talking about it's a little bit different. We still have our A, which is this bottom flat plane, but now we're looking at the location really of everything with respect to some sort of datum reference that looks like this. We're dealing with C as a location and B as a location. So we're dealing with the location of this hole or of this feature with respect to where this hole is. And so that in itself will change how this part is produced, or it could change, but it certainly changes the intent. This corner and this corner aren't as important anymore as this corner is on this particular part. So it's the same part, but the intent changes some. I'd also like to note here that if you've gone over my maximum material condition or material condition modifier video, you will notice that B, datum B here, is a feature of size. And since B is a feature of size, it has a size, it has a maximum material condition and a least material condition position, right? It could be made at the maximum material, which is the smallest hole. It could be made at the least material condition, which is the largest hole. And so with this, we could add these to the reference frame. Now by adding maximum material condition in this example, so we would have A, C, and then we were going to deal with B at maximum material condition, changes how we're going to deal with the locations of these other parts. All right, as I look through some different things here, the only other kind of detail I want to talk about, and it's really just a vocabulary issue, is that when we have our datums, so we have our feature, take these out, and we reference features that are datums. So these are the features of the parts, so these are our datum features. When we deal in our reference plane, so this is our example of a reference plane, these surfaces are simulated datum features. And so they're what we are using to theoretically simulate the perfect datum. And so they are said to be perfect. And so as such, that'll be a term that you hear. The second thing that I want you to understand is that when we are dealing with datum features, we are dealing with features. And so a part like this, although designed with an axis going through the center, we do not define the axis as the datum. Now hold on, don't get too excited there. So what I mean by that is that we don't label the axis going through the center of this part as the datum. If we were to use this or this slot as a datum feature, we do not label the plane that the feature makes as the datum. We don't put the label on the plane. We put the datum on the surface. Now, because we're doing that, we are referencing that plane in this case. Or if we pick this cylinder, let's just pick this little feature here, we are picking its axis as our reference axis. Although this isn't the best example because it doesn't have a lot of features going through this axis, what we need to remember is that for the produced part, the axis that this surface creates may be, more than likely could be, depends on how the part gets built, different than the axis created by this surface. Those are two different axes. So in design, we cannot label a singular axis just off in space and say, I want this center axis to be our datum reference, because we don't know. Is it the axis made by this surface? Is it the axis made by this surface? Is it the axis made by both surfaces as what we would call a continuous feature? We consider this one feature. And on a last note, as you go through and establish datum reference frames for your parts, try not to over-constrain your models. And so things to consider, is attaching a datum reference on this surface and attaching a datum reference on this surface at the same time, and then trying to use that as control, really it over-constrains the part. We're removing the degrees of freedom in this part in the same way, and so then we will struggle to understand what in the world you mean by that. All right, so hope you enjoyed this. Hope you have a good day. We'll see you next time.